Hello everyone, welcome to AI Crack channel and this is Set Theory Lecture 2. So today we'll be studying laws of sets and operations on sets. So let's directly jump into the discussion. So this is question of the day 3. You can pause the video, you can take a screenshot, whatever. The solution will be provided tomorrow. Let's start with the operations on sets. Let's first discuss about union of sets. A union B, this is represented by this symbol, the upper cup. And mathematically it means X belongs to either A or X belongs to B. So basically it is a bigger set which has elements of both A and B. So what does this mean? Let's say this is our set A, this is set B, and we have elements of A over here, some overlap between A and B, and these are the elements of B. So diagrammatically this is being represented by this one. This entire region is being presented as A union B. Basically it has both elements of A and B. Now the interesting thing is there is some overlap over here, and as we all know that we cannot repeat the elements in sets, so that's why we have done like that. Let's take an example. A equals to 1, 2, 3 and 4. Let's say B equals to 2, 3 and 5. So we can see that we have overlap of 2 and 3. 2 or 3 are common. In case of A union B as a set, we can write 1, 2, 3, 4 and 5. So we have written 2 and 3 just once. So that belongs to this overlapped region. Now talking about intersection of sets. So this is specifically this overlapped region. This is set A, this is set B, and it mathematically means X belongs to A and X belongs to B. Basically, we have to find the common region, common elements between A and B set. Let's take an example again. This is 1, 2, 3, and 4. Sorry. Yeah. And let's say B equals to 2 and 3. So we can see that 2 and 3 is common over here. So this region belongs to 2 and 3. This is 1 over here and 4 over here, and there is nothing over here. So 2 and 3 belongs here, 1 and 4 belongs here, nothing belongs here. So this is basically intersection of sets. So these definitions are quite boring. So we'll get a feel of that when we do the examples. Now let's look at difference of two sets, which is represented by A minus B. So this basically means X belongs to A and X doesn't belong to B. So let me mark it first. So this region is diagrammatically represented as A minus B. So what does that mean? This is set A, this is set B. We have to include all those elements of A which are not present in B. So basically, these are the elements which are common in A and B. So we don't have to include these elements. We have to take all the elements of A which are not common with B. So let's take an example first. So this is 1, 2, 3, and 4 in set A, and let's say B is 2 and 3. In that case, A minus B is, so 2 and 3 is common over here. So we have to take only those elements which are not in B. So 1 and 4. 1 and 4 is not present in B. So that's why we have taken that. This is also presented as A intersection B dash. So what does that mean? So let's say this is A, this is B, and we know that this is B dash, right? Yes, this is B dash. Now we have to intersect it with A. So let me mark it this way. So you can see that again we get that we get again this region, this particular region, the checked one, right? Now let's look at symmetric difference of two sets. Basically A delta B. This is presented by A delta B, and what this means is A minus B union B minus A. So taking the example from the previous one, so this is A minus B and the reverse is B minus A, and union of both of these means this region, right? So excluding this region, so this is nothing but A union B and subtract A intersection B, right? We can do that. A union B is the entire region and we can subtract A intersection B from it. and this is also presented by this one. So both of these methods are correct. Now let's talk about complement of a set. So this is, let's say, set A. So we can see that this is complement of a set, which is presented by A dash. So mathematically it means X doesn't belong to A, but X belongs to universal set. So U minus A basically. Basically it means all those elements of universal set except those which are present in A. So that is nothing but U minus A. It is also presented by A dash. Disjoint sets. I have made the diagram incorrect. So let's make the correct diagram over here. Disjoint sets mean there is no common element in between these two sets. Let's say this is set A, this is B. So let's say this is 1 comma 2 and B equals to 3 comma 4. So we can clearly see that there is no intersection point. There is no common element in between those sets, in between these two sets, right? So that's why these are called disjoint sets. So intersection of these two sets is 5, nothing. Now let's look at this example. This is set A, this is set B, and we have to find B minus A minus B. So let's call this as C. So we have to find B minus C. Let's find C first, A minus B. So A minus B means all the elements of A excluding those which are present in B. So is 1 present in B? No. So that's why we can include it in this set. Is 2 present over here? Yes. 3 present over here? No. That's why included. 4, yes. 5, yes. And 8, yes. So we can clearly see that A minus B is 1 comma 3. Now we have to find B minus C. So this was C set. Now is 2 present over here? No. That's why we can add it over here. 4, no. 5, no. And 8, no. So that's why B minus C is this set, right? Now let's look at another example. Let A equals to this set. Find the total number of unordered pairs of disjoint subsets of A. So basically we have been given a set A equals to 1, 2, 3, and 4. So we have to find pairs of disjoint subsets of A. Basically we have to make this kind of scenario. So what kind of examples we can have over here? So let's say this has 1 and 2 and this has 3 and 4. So how to proceed for this question? Now let's talk about this element. This has 3 choices. Either it can go over here, or it can go over here, or it cannot go anywhere. How? Let's say this has just 1 and this has just 2. This is a singleton set 1, this is singleton set 2. This is still a subset of A, this is still a subset of B, A, and both of these are disjoints, but all these elements are not being utilized. Only 1 and 2 are being utilized to create the subsets. 3 and 4 are not being used. So that is why it has any element has always a chance that it cannot go anywhere. Not over here, not over here. Okay. So now this element has 3 options. It can go over here, it can go over here, or it can go, it doesn't want to go anywhere. Similarly with this one, similarly with this one, similarly with this one. So basically 3 into 3 into 3 into 3. So that is 81. Now what is happening? Let's look at one example. Let's say this has 1 and 2 and this is 3 and 4. Another case is there where 3 and 4 over here and 1 and 2 over here. But we have to find what? We have to find unordered pairs. Now this one, this pair and this pair, both of these are same because we are talking about unordered pairs. So we have to consider them as just 1. But we cannot divide 81 by 2 because that will give us decimal points. So why is that happening? Let's look at another situation. Now let's say none of the elements want to go in any of these sets, but that can happen only once. So this is not going anywhere, this is not going anywhere, this is not going anywhere, and this is also not going anywhere. So that can happen only once. It's not happening twice, right? So either what we can do 81 minus 1 by 2 and plus that null set, right? Or 81 plus 1 by 2, and that is the answer, right? So that's why these are correct answer. So why I did that? Because every element, every order, every pair was getting repeated, right? But in case of a null set, it was not getting repeated. So that's why either subtract it and add it manually, or add 1 and divide by 2. So both ways we can get the answer as D. Now let's start with the properties or laws of sets. So first one is commutative law. What does this mean is A intersection B equals to B intersection A, and A union B equals to B union A. So this is nothing but 1 plus 2 equals to 2 plus 1. Kind of similar thing, right? We can take the analogy from here. So let's look at the example first via Venn diagram. So let's say we are talking about A union B. So for that, we'll first mark this, and then we'll mark this one. This is A union B. When we talk about B union A, then we'll mark this, and then we'll mark this. So in both the cases, we are getting the same region. So that is why we can prove it via Venn diagram that commutative law holds true. Or you can take the analogy from here as well. Now talking about associative law, A intersection B intersection C equals to A intersection B intersection C. So basically, we are just moving the brackets. We can move the brackets as per our needs, as long as these signs are same. As long as these signs are same, we can move the brackets as per our convenience. How? Again, take the analogy from numbers. 1 plus 2 plus 3 is same as 1 plus 2 plus 3 is same as 1 plus 2 plus 3, right? So all these three means the same, but what is happening? The sign is similar. So we have to consider over here that this particular operation, not sign, operation is similar. Only in that case we can apply associative law. Let's look at the proof once. Let's talk about A intersection B. So let's say this is A, this is B, and this is C. So let's talk about A intersection B first. So A intersection B is this one. Now we have to intersect it with C. Let me change the color, and this region. So basically we got this region. Now let's do it B intersection C first. So this is A, this is B, and this is C. So B intersection C is this, and intersecting it with A, we get this region only, right? So in both ways, we are getting the same region. So that's why associative law, we can prove it by Venn diagrams. Now talking about distributive law, what does this say? We can again have the similar kind of analogy in numbers. So let's say we want to write 1 plus 2 into 3. So what do we do over here? This is 1 into 3 plus 2 into 3. That's what we do. So this is similar kind of thing over here. So A union B intersection C is nothing but this union is being distributed inside the bracket. A union B intersection A union C. So you can again prove it with the help of Venn diagram, but you can just remember it as well, right? Now talking about De Morgan's law. What does this say is A union B dash equals to A dash intersection B dash. So what is happening? If we are taking the dash over here, we cannot take the analogy over here because we have limited analogies from numbers. So this one is unique. A union B dash equals to A dash intersection B dash. So you can see that the sign is, the symbol or operator is being changed. Now let's look at the proof via Venn diagram. So this is A and this is B. So let's talk about A union B first. So we can clearly see A union B is this. Now what we have to do is we have to find the dash of this entire region. So let me use another marker. So we can mark it as here. This is A union B dash, the external region, right? Now let's look at this one. We have A dash intersection B dash. So this is set A, this is set B. Now A dash means this region. Now B dash B dash is this region. So you can clearly see that this intersecting region is the one which is same as this green marked region, right? So that is how we can say that A union B dash equals to A dash intersection B dash. We can also prove this one as well by similar kind of approach. Identity law. So basically this means that A intersection union is A. So this is very easy to understand. So this is our universal set, and let's say this is set A. Now if I'm intersecting this with the universal set, in that case we are going to get A only, because this is the common region between both universal and A set, right? So that's why this is anti-law. Now A union phi is also A. So basically we have this set A and we are adding another set B which has no element. So if there is no element, we are going to get this only, right? There is no element in B, so we are going to get A only. So you can visualize it via Venn diagrams. Complement law. A union A dash equals to universal set. So this is kind of very obvious, but let's look at it once. So this is A and the external region is A dash. So when I'm adding both the elements, we are sorry. So when I'm adding both the elements of A dash and A, so we are definitely bound to get the universal set. Similarly, A intersection A dash. So this is A and we have this as A dash. So we can clearly see that there is no intersecting point between A and A dash. So that's how they are being defined. So that's why it's phi, right? Now you can prove this one as well with the help of Venn diagram. So this is A, this external region is A dash, and external region to A dash is nothing but A only, right? So that's how this is being defined. Idempotent law. So I leave this for the students because they can prove themselves by the help of Venn diagrams. This is very obvious. Now let's look at one example. If A and B are two sets and A dash and B dash denotes complement of A and B respectively, then A union B intersection B dash equals. So this might be a lengthy question. Let's look at it. So we have A dash union B intersection B dash. So let me tell you that these are the kind of questions you need to practice for PGDBA. And we have seen few questions like this in the past in PGDBA examination. So make sure you understand these kind of questions, either with the help of Venn diagrams or with the help of laws. So let's look at it with the help of laws. You can do it with the help of Venn diagrams. That is the easier part. Doing it with the help of laws is the difficult part. Sorry. Now let's solve this one first. So this is A union B intersection B dash. So we can see that these two operators are not same. So we can apply distributive property. So this means A intersection B dash union B intersection B dash. So what do we know that B intersection B dash is nothing but phi, because there is no common element between B and B dash. So this becomes nothing but A intersection B dash union phi. Doing union of phi or any set, in that case we get the set only, right? We saw it recently. So this is nothing but A intersection B dash. A dash union A intersection B dash. Yes. Now we have got this. Now we can see that these two signs are different over here. So we again have to apply distributive property. So this is nothing but A dash union A intersection A dash union B dash, right? Now we know that A dash union A is nothing but universal set, because A dash union A. So these are two complements, and when we are going to add these two, so this is nothing but universal. We have seen that recently. have to intersect it with A dash union B dash. Now we again know that anything, if we are intersecting with universal set, we get the set only. So this is nothing but A dash union B dash. So basically this is nothing but we have to reverse the De Morgan's law, A intersection B dash, right? Yes, so C is the correct option. So today's lecture was still here only, and in the next lecture we'll study about cardinal numbers and Cartesian product and few examples. Yes. If you are enjoying the lecture series and the question of the day series, then do subscribe the channel and share it with your friends. Thanks for watching.